Food coloring or color additive is any dye, pigment or substance that imparts color when it is added to food or drink. They come in many forms consisting of liquids, powders, gels, and pastes. Food coloring is used both in commercial food production and in domestic cooking. Due to its safety and general availability, food coloring is also used in a variety of non-food applications including cosmetics, pharmaceuticals, home craft projects, and medical devices. Purpose of food coloring. People associate certain colors with certain flavors, and the color of food can influence the perceived flavor in anything from candy to wine. Sometimes the aim is to simulate a color that is perceived by the consumer as natural, such as adding red coloring to glacé cherries. But sometimes it is for effect, like the green ketchup that Heinz launched in 1999. Color additives are used in foods for many reasons including offset color loss due to exposure to light, air temperature extremes, moisture and storage conditions. Correct natural variations in color, enhance colors that occur naturally, provide color to colorless and fun foods. Make food more attractive and appetizing, and informative. Allow consumers to identify products on site, like candy flavors or medicine dosages. Food colorants, synthetic. Food colorants, natural. Regulation. Past use and regulation history. The addition of colorants to foods is thought to have occurred in Egyptian cities as early as 1500 BC, when candy makers added natural extracts and wine to improve the product's appearance. During the Middle Ages, the economy in the European countries was based on agriculture, and the peasants were accustomed to producing their own food locally or trading within the village communities. Under feudalism, aesthetic aspects were not considered, at least not by the vast majority of the generally very poor population. This situation changed with urbanization at the beginning of the modern age, when trade emerged, especially the import of precious spices and colors. One of the very first food laws, created in Augsburg, Germany, in 1531, concerned spices or colorants and required saffron counterfeiters to be burned. With the onset of the Industrial Revolution, people became dependent on foods produced by others. These new urban dwellers demanded food at low cost. Analytical chemistry was still primitive and regulations few. The adulteration of foods flourished. Heavy metal and other inorganic element-containing compounds turned out to be cheap and suitable to restore the color of watered-down milk and other foodstuffs. Some more lurid examples being red lead and vermilion were routinely used to color cheese and confectionery. Copper arsenide was used to recolor used tea leaves for resale. It also caused 2 deaths when used to color a dessert in 1860. Sellers at the time offered more than 80 artificial coloring agents, some invented for dyeing textiles, not foods. Thus, with potted meat, fish and sauces taken at breakfast, he would consume more or less Armenian bowl, red lead, or even bisulfurate of mercury. At dinner with his curry or cayenne, he would run the chance of a second dose of lead or mercury. With pickles, bottled fruit and vegetables, he would be nearly sure to have copper administered to him, and while he partook of bonbons at dessert, there was no telling of the number of poisonous pigments he might consume. Again, his tea, if mixed green, he would certainly not escape without the administration of a little Prussian blue. Many color additives had never been tested for toxicity or other adverse effects. Historical records show that injuries, even deaths, resulted from tainted colorants. In 1851, about 200 people were poisoned in England, 17 of them fatally, directly as a result of eating adulterated lozenges. In 1856, morphine, the first synthetic color, was developed by Sir William Henry Perkin, and by the turn of the century, Unmonitored color additives had spread through Europe and the United States in all sorts of popular foods, including ketchup, mustard, jellies, and wine. Concerns over food safety led to numerous regulations throughout the world. German food regulations released in 1882 stipulated the exclusion of dangerous minerals such as arsenic, copper, chromium, lead, mercury and zinc, which were frequently used as ingredients in colorants. In contrast to today, these first laws followed the principle of a negative listing. They were already driven by the main principles of today's food regulations all over the world. Since all of these regulations follow the same goal, the protection of consumers from toxic substances and from fraud. In the United States, the Pure Food and Drug Act of 1906 reduced the permitted list of synthetic colors from 700 down to 7. Even with updated food laws, adulteration continued for many years, and this, together with more recent adverse press comments on food colors and health, has continued to contribute to consumer concern about color addition to foodstuffs. In the 20th century, the improvement of chemical analysis and the development of trials to identify the toxic features of substances added to foods led to the replacement of the negative lists by lists of substances allowed to be used for the production and the improvement of foods. This principle is called a positive listing, and almost all recent legislations are based on it. Positive listing implies that substances meant for human consumption have been tested for the safety, and that they have to meet specified purity criteria prior to their approval by the corresponding authorities. In 1962, the first EU directive approved 36 colorants, of which 20 were naturally derived and 16 were synthetic. This directive did not list which food products the colorants could or could not be used in. At the time, each member state could designate where certain colors could and could not be used. In Germany, for example, quinine and yellow was allowed in puddings and desserts, but tartrazine was not. The reverse was true in France. This was updated in 1989 with 89/107 EEC, which concerned food additives authorized for use in foodstuffs. Current regulation. While naturally derived colors are not required to be certified by a number of regulatory bodies throughout the world, they still need to be approved for use in that country. The FDA lists color additives exempt from certification for food in Subpart A of the Code of Federal Regulations, Title 21, Part 73. However, this list contains substances which may have synthetic origins, such as nature-identical beta-carotene. FDA's permitted colors are classified as subject to certification or exempt from certification, both of which are subject to rigorous safety standards prior to their approval and listing for use in foods. Certified colors are synthetically produced and are used widely because they impart an intense, uniform color, are less expensive, and blend more easily to create a variety of hues. There are 9 certified color additives approved for use in the United States. Certified food colors generally do not add undesirable flavors to foods. Colors that are exempt from certification include pigments derived from natural sources such as vegetables, minerals or animals. Nature-derived color additives are typically more expensive than certified colors and may add unintended flavors to foods. Examples of exempt colors include annatto, beet extract, caramel, beta-carotene, turmeric and grape skin extract. Food colorings are tested for safety by various bodies around the world, and sometimes different bodies have different views on food color safety. In the United States, FDA and AMP-C numbers are given to approved synthetic food dyes that do not exist in nature, while in the European Union, E numbers are used for all additives, both synthetic and natural, that are approved in food applications. The food colors are known by E any numbers that begin with a 1, such as E100 or E161b. The safety of food colors and other food additives in the EU is evaluated by the European Food Safety Authority. Color Directive 94/36/EC, enacted by the European Commission in 1994, outlines permitted natural and artificial colors with their approved applications and limits in different foodstuffs. This is binding to all member countries of the EU. Any changes have to be implemented into the national laws within a given time frame. In non-EU member states, food additives are regulated by the national authorities, which usually, but not in all cases, try to harmonize with the laws adopted by the EU. Most other countries have their own regulations and list of food colors which can be used in various applications, including maximum daily intake limits. Global harmonization. Global trade requires harmonization of food regulations on a worldwide basis in order to abolish barriers of trade and to ensure that the economic and nutritional demands of all nations are considered. Since the beginning of the 1960s, JECFA has played an important role in the development of international standards for food additives, not only by its toxicological assessments, which are continuously published by the WHO in their technical report series, but furthermore by elaborating appropriate purity criteria, which are laid down in the 2 volumes of the Compendium of Food Additive Specifications and the supplements. These specifications are not legally binding but very often serve as a guiding principle, especially in countries where no scientific expert committees have been established. In order to further regulate the use of these evaluated additives, in 1962 the WHO and FAO created an international commission, the Codex Alimentarius, which is composed of authorities, food industry associations and consumer groups from all over the world. Within the Codex organization, the Codex Committee for Food Additives and Contaminants is responsible for working out recommendations for the application of food additives. The general standard for food additives, in the light of the World Trade Organization's General Agreement on Tariffs and Trade, the Codex standard, although not legally binding, influences food color regulations all over the world. Artificial coloring. As the 1900s began, a host of synthetic dyes and pigments became available. Originally, these were dubbed "coal tar colors" because the starting materials were obtained from bituminous coal. Many synthesized dyes were easier and less costly to produce and were superior in coloring properties when compared to naturally derived alternatives of the time, also known as azo dyes. Synthetic colors are generally produced via 2-step chemical synthesis. The first step forms a diazo compound from the reaction of aromatic amines generally formed from nitrosamine and a diazonium compound. The second step couples these diazo compounds with various reactive aromatic hydrocarbons. Due to the pi electrons across the 2 aromatic sections and the azo groups, a conjugated system exists that is able to absorb light of specific wavelengths, leading to the color of the compounds. The attractiveness of the synthetic dyes is that their color, lipophilicity, and other attributes can be engineered by the design of the specific molecule. The color of the dyes can be controlled selecting the number of azo groups and various substituents. Yellow shades are achieved by using acetoacetanilide and heterocyclic compounds. Red colors result from the reaction between an aniline derivative with a naphthol derivate. A blue results from replacing the aniline derivate with a benzidine derivate. The pair indigo and indigo carmine exhibit the same color, but the former is soluble in lipids, and the latter is water-soluble because it has been fitted with sulfonate functional groups. In the United States, only 7 dyes were initially approved under the U.S. Pure Food and Drug Act of 1906, but several have been delisted and replacements have been found. Some of the food colorings have the abbreviation FCF in the names. This stands for coloring food, or the coloring of food. In the United States, manufacturers must get FDA approval for every batch of certified colors produced. FDA personnel evaluate the color's physical appearance and chemically analyze it. Tests include purity, moisture, residual salts, unreacted intermediates, colored impurities other than the main color, any other specified impurities, and heavy metals. The results are reviewed for compliance with the identity and specifications described in the listing regulation for the color additive. If the sample is found to meet these requirements, the FDA issues a certificate for the batch that identifies the color additive. For example, a batch of tartrazine becomes FD&C yellow no. 5. Current 7 generally permitted. In the U.S., the following 7 artificial colorings are generally permitted in food as of 2016. The lakes of these colorings are also permitted except the lake of red number 3. FD&C blue number 1 brilliant blue FCF E133. FD&C blue number 2 indigotine E132. FD&C green no. 3 fast green FCF E143. FD&C red number 3 erythrocene E127. FD&C red no. 40 allura red AC E129. FD&C yellow no. 5 tartrazine E102. FD&C yellow no. 6 sunset yellow FCF E110. Permitted for limited use in foods. 2 dyes are allowed by the FDA for limited applications. Citrus red 2 allowed only to color orange peels. Orange B allowed only for use in hot dog and sausage casings. Delisted and banned in the US FD&C red no. 2 amaranth E123. FD&C red no. 4. FD&C red no. 32 was used to color Florida oranges. FD&C orange number 1 was one of the first water-soluble dyes to be commercialized, and one of 7 original food dyes allowed under the Pure Food and Drug Act of June 30, 1906. FD&C orange no. 2 was used to color Florida oranges. FD&C yellow number 1, 2, 3, and 4. FD&C violet number 1. Approved in EU. E-numbers chapters 102 to 143 cover the range of artificial colors. For an overview of currently allowed additives, see here. Some artificial dyes approved for food use in the EU include E104 quinol and yellow, E122 carmazine, E124 ponceau 4R, E131 patent blue V, E142 green S natural food dyes, carotenoids, chlorophyll and anthocyanins, and betanin comprise 4 main categories of plant pigments grown to color food products. Other colorants or specialized derivatives of these core groups include annatto, a reddish-orange dye made from the seed of the achiote, caramel coloring made from caramelized sugar, carmine, a red dye derived from the cochineal insect Dactylopus coccus, elderberry juice, lycopene, paprika, turmeric, Blue colors are especially rare. To ensure reproducibility, the colored components of these substances are often provided in highly purified form. For stability and convenience, they can be formulated in suitable carrier materials. Hexane, acetone, and other solvents break down cell walls in the fruit and vegetables and allow for maximum extraction of the coloring. Traces of these may still remain in the finished colorant, but they do not need to be declared on the product label. These solvents are known as carryover ingredients. Dyes and lakes. Color additives are available for use in food as either dyes or lake pigments. Dyes dissolve in water, but are not soluble in oil. Dyes are manufactured as powders, granules, liquids or other special-purpose forms. They can be used in beverages, dry mixes, baked goods, confections, dairy products, pet foods, and a variety of other products. Dyes also have side effects that lakes lack. Consuming large amounts of dyes can color stools. Lakes are made by combining dyes with salts to make insoluble compounds. Lakes tint by dispersion. Lakes are not oil-soluble, but are oil-dispersible. Lakes are more stable than dyes and are ideal for coloring products containing fats and oils or items lacking sufficient moisture to dissolve dyes. Typical uses include coated tablets, cake and donut mixes, hard candies and chewing gums, lipsticks, soaps, shampoos, talc, etc. Other uses. Because food dyes are generally safer to use than normal artists' dyes and pigments, some artists have used food coloring as a means of making pictures, especially in forms such as body painting. Red food dye is often used in theatrical blood. Most artificial food colorings are a type of acid dye, and can be used to dye protein fibers and nylon with the addition of an acid. They are all wash fast and most are also light fast. They will not permanently bond to plant fibers and other synthetics. Criticism and health implications. There is no evidence to support broad claims that food coloring causes food intolerance and ADHD-like behavior in children. It is possible that certain food coloring may act as a trigger in those who are genetically predisposed, but the evidence is weak. After concerns were expressed that food colorings may cause ADHD-like behavior in children, the collective evidence do not support this assertion. The US FDA and other food safety authorities to regularly review the scientific literature, and led the UK Food Standards Agency to commission a study by researchers at Southampton University of the effect of a mixture of 6 food dyes on children in the general population. These colorants are found in beverages. The study found a possible link between the consumption of these artificial colors and a sodium benzoate preservative and increased hyperactivity. In the children, the advisory committee to the FSA that evaluated the study also determined that because of study limitations, the results could not be extrapolated to the general population, and further testing was recommended. The US FDA did not make changes following the publication of the Southampton study, but following a citizen petition filed by the Center for Science in the Public Interest in 2008 requesting the FDA ban several food additives. The FDA reviewed the available evidence, and still made no changes. The European regulatory community, with an emphasis on the precautionary principle, required labeling and temporarily reduced the acceptable daily intake for the food colorings. The UK FSA called for voluntary withdrawal of the colorings by food manufacturers. However, in 2009 the FSA re-evaluated the data at hand and determined that the available scientific evidence does not substantiate a link between the color additives and behavioral effects for any of the dyes.